In the previous lecture, we followed the evolution of high-mass stars, stars in excess of 4 times the mass of the Sun. If the mass of the star was between 4 and 8 times the mass of the Sun, it would end its life relatively peacefully as an oxygen neon magnesium white dwarf, ejecting most of its mass in the form of a brief planetary nebula, which then mixes out into the interstellar medium. If the mass is in excess of 8 times the mass of the Sun, its evolution is very different. The last years of a massive star's life see it burning through a succession of increasingly inefficient nuclear fuels. It burns through these fuels in an attempt to meet its enormous luminosity needs and so maintain a state of thermal equilibrium. Hydrogen fusion into the core can proceed stably for approximately 10 million years in a massive star. Helium fusion into carbon and oxygen can only proceed stably for about 1 million years because of its increasing inefficiency. Carbon fusion is more inefficient still, and carbon fusion into oxygen, neon, and magnesium can only proceed for approximately 1,000 years before the available carbon in the core is exhausted. At this point, if the star is between 4 and 8 times the mass of the Sun, it will end its life as an inert oxygen neon magnesium white dwarf. However, if the star exceeds 8 times the mass of the Sun, this oxygen neon magnesium core can collapse, and it can fuse neon into heavy elements, which can occur for only about 5 years, oxygen for only about 1 year. Neon and oxygen fusion mark the point at which losses due to neutrinos start becoming larger and larger, and less of the fusion energy released is actually in the form of photons that are available for making up for the star's enormous luminosity losses. It gets even worse at the end of the oxygen fusion phase, in which a heavy silicon core is formed, and when silicon fusion ignites at billions of degrees Kelvin, it can only make up for the star's energy needs for 1 day before it too is exhausted. The end product of silicon fusion is iron and nickel, and so at the end of the silicon fusion day, the star will have built up an enormous inert iron-nickel core at its very center. When silicon fusion runs out after 1 day, the inert iron-nickel core is approximately 1.5 and 2 times the mass of the Sun and is packed inside of a volume the radius of the Earth. The core temperature is 10 billion grams per cubic centimeter, and the core temperature exceeds approximately 10 billion degrees Kelvin. At this stage, by the time it forms an inert iron-nickel core, there are no more sources of fusion energy available to the star that will generate energy. All further fusion will lead to the loss of energy, will actually require energy to proceed, and so the star is out of nuclear fuel. The inert iron-nickel core is no longer able to hold itself up against the crush of gravity. It becomes unstable, and it begins to start a collapse. But this time, the collapse is final, and it is catastrophic. The way to think about what has been going on within the star for the last 10 or 11 million years is a star needs to make up for its energy loss due to shining away starlight. The rate at which it loses energy is given by its luminosity. In a very massive star, all of the subsequent evolution of a star, from the time it alights on the main sequence, at the zero-age main sequence, when it starts beginning to get all of its energy from hydrogen fusion into helium, until the stage that we've reached now, the star is more or less at the same luminosity. It's slowly crawling up in luminosity, but only for a very, very brief period. The way to think of it is this. The star is holding off gravitational collapse. It's got an enormous amount of gravitational potential energy, and yet it has been borrowing for the last 10 or 11 million years against nuclear binding energy in order to stave off the moment in which gravity is finally going to win its long-standing tug-of-war with pressure and cause the star to collapse. As each successive nuclear fusion fuel is brought into play, it is less and less efficient. The star, in a sense, is becoming more and more desperate to try to stave off the gravitational collapse, slowly but surely building up an enormous energy deficit. That energy debt is now been called to be paid, and the star is going to have to pay it in a few seconds. At the onset of iron-nickel core collapse, energy-consuming processes begin to kick into play that begin to accelerate the collapse. The first of these is photodisintegration. At temperatures exceeding about 10 billion degrees, high-energy photons are sufficiently energetic that they actually exceed the binding energy of the atomic nuclei themselves. The nuclei in the very center begin to melt into helium, protons, and neutrons, reversing more than 10 million years of nuclear fusion. A high-energy photon striking an iron-56 nucleus will break it up into a whole bunch of helium nuclei. Other nuclei, as they break apart, will break into helium nuclei, the tightest bound light nucleus, protons, and neutrons. Once you begin to have a large number of protons and electrons, the process of neutronization begins. In neutronization, the protons and electrons collide and combine, forming a neutron and a neutrino. It's this neutrino formation that is critical for what happens next. The neutrinos try to escape from the star and carry off energy. They start out radically altering the energy balance inside the nucleus. So what used to be a way of building up thermal energy inside of the core, that thermal energy going into the pressure that supports the core against gravity, has now had the rug pulled out from underneath it. Photons, which should have been in the thermal bath, are now being burned up, causing nuclei to melt. And when the electrons and protons from that nuclear melting begin to form into neutrons, they carry off additional energy in the form of neutrinos. The collapse begins to radically accelerate. The iron-nickel core collapse is rapid and catastrophic and takes only about 1/10 of a second. The processes that I'm now going to describe take me longer to describe than actually happen in nature. The initial phase begins when the iron-nickel core is about the radius of the Earth, about 3,000 kilometers in radius, at a density of about 10 billion grams per cubic centimeter. It is rapidly falling inwards, and it is made of nearly pure iron and nickel surrounded by a silicon-burning shell. The first thing that happens is neutrinos begin pouring out of the system. 1/10 of a second later, the radius has gone from 3,000 kilometers to 100 kilometers, and the density has climbed from 10 billion to 1 trillion grams per cubic centimeter, 10 to the 12 grams per cubic centimeter. At this point, we begin melting into a sea of heavy nuclei, and the neutrinos begin to be trapped in the collapsing core. Up to this point, we have treated neutrinos as essentially ghost particles. They carry energy and mass away from the star because the star practically doesn't even exist to them. However, once the density exceeds about 10 to the 10 or 10 to the 11 grams per cubic centimeter, that's no longer true. And by the time it reaches 1 trillion grams per cubic centimeter, the material starts to become largely opaque to neutrinos. This means that neutrinos that up to this point were attempting to carry away energy begin to be trapped in the core. As the neutrinos are trapped, they give up their energy to the core, and the core's energy starts to pick up. But at this point, it's too late for that energy pickup to halt the collapse just yet. The core continues to collapse until the density reaches 2 to 3 times 10 to the 14 grams per cubic centimeter. 2 to 300 trillion grams per cubic centimeter. At this point, the density of the matter in the core, which constitutes about 1.5 solar masses worth of material, has the same density as an atomic nucleus. The radius has now shrunk to 10 kilometers, and it has done so within 100 milliseconds. The surface of the core is moving at a speed of nearly 1/10 the speed of light. At this point, the rules change dramatically. The strong nuclear force now comes into play because we've crushed 1.5 solar masses of nuclear material down to the point that it is the same density as an atomic nucleus, and now the dominating force and the dominating interaction between the particles is no longer the long-range force of the electromagnetic force, but now is the short-range, strong nuclear force, the same force that appears inside of atomic nuclei and helps bind them together. At this point, the collapse comes to a screeching halt. The inner core basically stops collapsing almost immediately, but it overshoots a little bit, getting smaller in radius, and now the strong nuclear force is stronger than gravity. And once it stops, it's like cocking a spring, and when it stops, bounce, it releases. And the outer surface of the star suddenly smashes out into a core that begins moving outward at a speed of nearly 1/10 the speed of light. The core is 10 kilometers across. It has a mass of around 1.5 times the mass of the Sun. And the surface of that core, which is at an enormous density of nuclear matter of 200 to 300 trillion grams per cubic centimeter, suddenly slams into all of the gas and material that's attempting to fall into it. The bouncing core sends an enormous shock wave out into the infalling stellar envelope. The energy in this shock is prodigious. The energy is estimated to be in excess of 10 to the 44 joules. That is more energy than the Sun radiates over its entire 11 billion year lifetime. After nearly 50 milliseconds, the shock wave, which has been plowing out, plows up its own mass, and once it does so, the shock stalls. And at this point, in all the furious activity going on in the star, there's a brief instant of calm. The shock wave, which had been smashing out at 1/10 the speed of light, suddenly, slowly grinds to a halt. The neutrinos that were down inside that post-shock core begins to bounce out and pour out of this nucleus, in which the protons and electrons deep inside that post-bounce core are rapidly turning themselves into neutrons with emission of neutrinos. Some of these neutrinos carry energy away from the star, but most of them go into heating the gas and begin driving violent convection. What you've got deep inside the star is the post-bounce core, maybe 10 kilometers across, containing matter at nuclear density that's rapidly neutronizing. The neutrinos produced by the rapid neutronization are pouring out into the surrounding material, but that material is so dense it is mostly opaque to the neutrinos. They dump all of their energy, or much of their energy, down into the base of the infalling material just behind the stalled out shock. You've got a hot base and a cool-ish top. We're still talking about temperatures of billions of degrees, but now the temperatures are driven to nearly 100 billion degrees in some places, with a very hot bottom. When you have a hot bottom and a cool top, you begin to drive violent convection. But this is driving violent convection into extremely dense, extremely hot nuclear matter. After about 1 second, the shock wave dumps enough energy into the system to revive the shock wave, and the shock goes from stalled to beginning to blast its way outward. The neutrino turbulence basically drives a powerful neutrino wind through the shock waves that pushes the shock wave and smashes out through the envelope of the star. In the wake of this enormous shock wave, there is explosive nuclear fusion that is producing heavy elements like nickel, cobalt, and iron. A rapid neutron wind probably kicks into play at this point that begins to form even heavier nuclei as the neutrons and neutrinos began to pour into the material, blasting its way out of the star. Meanwhile, the shock wave, which has been revived, begins to push its way through the star's envelope, which you'll remember the outer edge of that envelope is out around the orbit of Jupiter, about 5 astronomical units from where all this is occurring. The traverse of the shock wave takes many hours, but eventually it breaks free of the surface, and when it does, we see an enormous supernova explosion. This is a video of the core bounce and collapse. It's been slowed down to show you the events of 1/3 of a second. The core stalls, the shock stalls, and now the neutrinos smashing into the material behind begins vigorously boiling until eventually the boiling produces enough energy deposition that all of a sudden it explodes outwards and the shock is revived. On larger scales, We can now follow this for many seconds as the shockwave begins to blast its way out through the red supergiant envelope. And now you'll see the clock in the upper right-hand corner accelerate as we now go through many minutes of evolution. The explosion drives the outer envelope away, pushing out the entire envelope, which previously extended to 5 astronomical units. As these various fingers of material smash into the surrounding stellar envelope, it begins to invoke enormous helium-hydrogen fusion all the way up the chain through heavy elements, eventually blowing off the entire envelope. From the outside, the explosive drive-off of this envelope results in a supernova explosion. A star, which only a moment before may have been a quiet red or blue supergiant, suddenly brightens in it within minutes to more than 10 billion times the luminosity of the Sun, easily outshining an entire galaxy containing hundreds of billions of stars for many weeks. The envelope is blasted off at speeds approaching 10,000 kilometers per second or more, a substantial fraction of the speed of light. And of the remnant core that was left behind, well, the post-core remains, 1.5 solar masses, doing something pretty interesting that we're going to talk about in a later lecture.